Hi, everyone. Welcome. So I guess I want to start with a quick poll here, just to get an idea of who's in the audience. So how many of you showed up because we put OpenStack in the title? Okay, a couple of people. How many of you showed up because OpenShift is in the title? Okay, what about the medical image processing part? Are you in healthcare? Do you actually, this is great. So are you actually in healthcare? Do you actually do medical image processing as part of your work? So how many of you are just healthcare related? Okay, what about, do you actually do stuff related to medical image processing in your jobs? Okay, so in the healthcare field at least. That's great. That'll help a lot. So just to give you an idea, so I hope most of you saw yesterday Dr. Ellen Grant talking with our CEO, Jim Whitehurst, about the ChRIS project, and that's what we're going to deep dive into a little bit here. We'll tell you a little bit about the ChRIS project itself, and a lot about how ChRIS uses Red Hat technologies to be able to do its job. So up on stage here, we have three groups represented. So we have Rudolph here from Boston Children's Hospital, which is the leading children's hospital in the US, and Ada from the Massachusetts Open Cloud, which is a very unique computing facility. We'll talk about both of those here through the presentation. So I should start by saying that I am in no way an expert in medical image processing. I started working on this project with Ada and Rudolph and other folks about a year ago. And everything that I might say that sounds like I know something about medical image processing, it almost certainly came from Rudolph and the other folks in the project. So if you do want to deep dive into that topic, Rudolph is a much better person to talk to. But what I have experienced, I guess, in that past year is I have met a lot of people in the space, people who are building the actual medical image processors themselves, and every single one of them, to a T, is an incredibly brilliant person. They are trying to solve, in every case, a very particular problem. So it might be something like trying to measure brain volume based off of an MRI. And the thing is, while that's a very difficult problem to solve, every single one of them is essentially trying to advance the field in some way by trying to solve that problem more accurately than it's ever been solved before. In each of those cases, though, the people are not really incentivized to build a system that is necessarily easy for someone else to run, or do it in a way which ever really will leave the lab that they're running inside of. And so what tends to happen is each of those people tend to build their own platforms. They get whatever results they get. They might use it within their own research institutions. But even if the code that they've written is open source, it's very likely that the next person that comes along is not going to start from that code base. They're going to start from something else because the way that the first person built it was not meant to pass along and better the ecosystem. So my name is Dan McPherson, and I am a software engineer from Red Hat.
All right, good morning, everyone. So over at Boston Children's, we've been developing this system that we've now come to call ChRIS for a couple of years now. And the first versions of ChRIS lived on a couple of laptops and workstations, and eventually spread to an HPC. And now in its current version, it's actually spreading to the cloud, and that's where the collaboration with Red Hat and the MOC comes to play. So in a nutshell, what the point of ChRIS was to make it easy for people to run any kind of medical imaging-based compute. It's comprised of a whole bunch of open source projects. These are kind of containerized, kind of microservices that communicate with each other with REST APIs. I want to leverage a little bit of what Dan just said about reinventing the wheel. That is a real problem in computational research. People are always writing the same backend over and over again. And one of the reasons this happens is because there's no reward in research to write a good system. The only thing that really matters is getting some kind of result. And it doesn't matter if this takes a week to get the result or not. Getting a paper, applying for grant funding, that's kind of the cycle that works. So now we began to realize that this actually is a barrier to innovation. You can only innovate so far if you're always working on the infrastructure. So what we've been trying to do is to make the infrastructure a solved problem for a researcher. So what we're trying to do is develop a community around this kind of ChRIS infrastructure. And we want to be able to ultimately get to a point where we can process data very, very quickly and get it out of the hospital onto the cloud, do some very fast compute, pull it back into the hospital, and put it kind of in front of a clinician who needs that information very, very quickly. Seconds and minutes is much, much better than hours or days or weeks. So we really tried to make imaging research clinically relevant as well. There is about 2 decades worth of amazing tools that exist in the research community, but these almost never make it out onto the clinical front lines. And this isn't just because of FDA regulations and stuff. It's really because no clinician is ever going to fire up a Linux terminal, type in some commands, figure out SSH and SCP and log into a cluster. That's never going to happen. We have to make it easy to have this compute happen, drop dead simple with a UI, click, 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 done, and finished. So that's the vision of this project. Oh, sorry. I'm Rudolf Pinar. I'm a staff scientist at Boston Children's Hospital.
All right, I'm going to talk a little bit about Massachusetts Open Cloud. This framework is running on our cloud. And Massachusetts Open Cloud is, or like MOC, is a very unique entity. We are a collaboration between academy, industry, and the government, which you don't see often, specifically Boston University, Northeastern University, UMass, Harvard, and MIT came together and built a data center to be able to do research and innovation on the cloud. And they figured out that to be able to do real research, you need to have a real environment and real production scale workloads. So that's how MOC started. And then with the support from Commonwealth of Massachusetts and the US Air Force and the industry partners, most notably to Sigma, Intel, Cisco, Lenovo, NetApp, Brocade, and Red Hat, we formed the MOC consortium. And when I say production scale, I want to mention a little bit about our infrastructure. We are operating over a data center that is 15 megawatts of that has a capacity of 15 megawatts, and we have 2 acres of compute space. So just to give you a perspective, our data center is around half of the size of an average Google data center. So that's even though MOC is not using the whole data center as of now, we have that capacity to utilize. MOC's mandate is slightly different, or totally different, I should say, from these big players like Amazon, Microsoft, Google in the public cloud space. You want to build a public cloud from the ground up using a wholly transparent and open ecosystem of cloud services. And we are, in some sense, a small-scale, tightly knit, open-source community because different parts of the cloud are being developed and maintained by different researchers across the universities and across these industry partners. And one of the other side of the coin for us is not only the infrastructure, but also the having production scale workloads on our cloud. And that's why we are very much interested in the healthcare space. We believe that, as Dr. Grant mentioned in her keynote speech, we believe that hospitals will not be able to maintain and analyze their data because they are generating more and more data, and these applications have to move to the cloud. And we want to have healthcare applications running on MOC so that we can have more industry-level applications on our system that we can analyze and learn from. That's why we are interested in the healthcare space in general and in the ChRIS project specifically. And our collaboration with Rudolf started 3 years ago. He kindly accepted to mentor a group of students in one of the classes that I teach in Boston University and Northeastern on cloud computing. And that initial proof of concept implementation, which tried to bring ChRIS platform to MOC, is now, in the last year, especially with the involvement of Red Hat, is now turning into a product that other people can use. And now we are trying to build a community around it. And we are also learning that from Red Hat as well. So Red Hat has been very enabling in that sense as well, not only from technology side, but also learning how to do open source, how to build open source communities. My name is Atatürk. I'm leading the healthcare analytics and big data analytics efforts in the Massachusetts Open Cloud. And I'm also a member of the Boston University in the electrical computer engineering department.
Yeah, so from a Red Hat perspective, we got involved in this project because it was a very interesting use case for us that we actually have a difficult time finding inside of the company. Namely, being able to utilize some advanced technologies that we'll talk about in detail here, but things like GPUs, where if you look inside of Red Hat, the use cases just don't really exist. And so we sought out these use cases to be able to try and sort of make a difference in the world, while at the same time being able to prove out our entire technology stack from end to end, and hopefully do that in a way which makes it easier for the next person that comes along. As a group, though, we have a few combined goals that we're trying to accomplish. So the first of those is, if you look at a lot of these medical image processing applications, they can take as long as a day or more to run in some cases. And so that tends to make them so that they become not clinically relevant. So it's something that becomes a process that's for the lab, but not something that necessarily a patient will ever see the results from. Or if they do, it's a pretty tedious process of the patient will first get the images taken and then have to come back days later to actually find out what the results were. And so what we're doing is using OpenShift and OpenStack to be able to provide a platform which is capable of enormous scale to be able to take the image processors and run them on many, many instances simultaneously, as well as using more advanced hardware, things like GPUs, like I just mentioned. The other main goal that we're trying to accomplish here is really democratizing the application development for these image processors. And again, it's about creating an ecosystem, a place where anyone who wants to build one of these processors, they know they can go, they can create the logic to be able to run at scale, and do so in a way which has a chance of running in more than just one location. So not only will it have a chance of running in this particular instance, but it's a generic platform that as long as you can run OpenShift and OpenStack, you'd be capable of recreating this anywhere. So we wanted to deep dive a little bit into the technology here and exactly what we're using. The first component, we're obviously using OCI and Docker for the ChRIS platform itself. So ChRIS itself, everything is built as OCI images. But the more innovative piece, or the part that really matters here, is that OCI Docker were chosen as the standard for which the image processors are also written as. This makes it so that it's very easy for someone to take an existing application, port it into a Docker image, and then get the portability to be able to run that essentially anywhere. And so from a development perspective, they can run it off their laptop. From a production perspective, that same image, they can run it in a production environment. The next component here is OpenShift and Kubernetes. The primary piece that we're using from OpenShift is the scale job framework. And that lets us, which we'll talk about this in some detail, but that lets us take an image processor and scale it from either one instance or essentially infinite instances, depending on the size of your cluster. Now, we're also taking heavy advantage of the resource management capabilities inside of OpenShift. It's a very big scheduling problem of how do I take image processors and decide which ones get priority over others, what sorts of scale are they allowed to run at. It's one of the big things that we've worked on, and adding to ChRIS is the ability to, as both a plugin writer or an image process writer, as well as an administrator of the cluster, deciding exactly what priority each item gets when it runs in the system. And then, as usual, OpenShift really brings a lot of operational characteristics to it, things like standardizing what it means to get logs and metrics for each of the image processors, as well as Ansible to be able to manage the cluster as a whole.
Yeah, I want to mention in MOC we make heavy use of OpenStack and OpenShift, and especially the ability of OpenShift to optimize for density and utilize Slack resources is very important to us in MOC. In MOC, like potentially any other cloud, we have a set of resources that are reserved and a set of resources that are free, not used. And OpenShift enables us to, and also, of course, some of these reserved resources are consumed, fully utilized, and some of them are not utilized. They are Slack resources in some sense. And OpenShift enables us to exploit these Slack resources and schedule jobs on not only free resources, but also on these Slack resources, improving the density of our cloud. And this matters to ChRIS application because we can now scale the ChRIS application not only on our free resources, but we can enable it to utilize more resources than is free available in that sense. But of course, this requires the application developer to be aware of utilizing this option of utilizing Slack resources. So a change in the mentality of application development is required, and part of the ChRIS project is bringing that awareness into the healthcare application developers, showing them if they design their applications to be able to exploit this opportunity to improve their performance, to improve the performance of their applications.
Yeah, and so the other area of overlap here between OpenShift and the ChRIS project comes around some newer technologies in artificial intelligence and machine learning. So at Red Hat, this is an area we've been doing a ton of research on lately. So there's projects like RAD Analytics that are out there that have been proving out technologies like Spark and TensorFlow running on top of OpenShift. This same area has a lot of overlap with what's happening in the image processing space as well. Rudolph here can talk to you afterwards if you want to dig into the details there. But essentially, large amounts of research are happening to use ML-type technologies in the image processing space. It is pretty early, though. There's not a lot of ML being used in production scenarios, but everyone can see that's sort of the way that it's heading, and a lot of innovation is happening there.
So Kubernetes and OpenShift do not directly solve the core underlying infrastructure problem, the classical infrastructure needs of compute, networking, and storage, and providing a scalable platform to run these applications is handled by OpenStack in our own platform, and we are very happy with OpenStack because not only because of its open source nature, but it's also because of its modular nature. Using OpenStack, different research teams in the MOC can work on different components and make it provide solutions and innovation in the cloud space and make it available to the upstream community, to a larger community than a set of researchers. And that's very important to us because we want to be able to not only do one-off research, but we want to be able to do research that has an impact. And that's why we are very much happy with the way that OpenStack is in general designed and how we can innovate in different components across different research groups.
All right, so let me go up the stack a little bit and just show you some examples of the kind of processing that now we can do on this backend. So these examples are typical that you would find in image processing in the medical field. The first one is registration, which is where you take one image and you match it into the space of another image. And that is very important to do because this is usually used to take ground truth that you have in a template and discover where that might be in the image you're looking at. It's also a measure of difference between two different image sets. And also importantly, if you have acquired multiple images and you want to compare them with each other, the first thing you typically have to do is register them to some common space. Oftentimes, some images might be skewed this way or a different angle or whatever the case may be, and you can't do meaningful compute unless you have them all lined up correctly together. And registration typically looks like this. You have an original image, and to show you over here, this is just a single slice. This is a whole volume that you actually register. This is one of many slices. Here's a template, and you merge this one onto here to put it into a common space to do further processing. Another hot topic that's developing right now, of course, is classification with AI and ML. And just to show you over here, the idea would be to have some image recognizer classify, figure out that here's a tumor. But you have different contrasts as well, different scans. And if you look very carefully, you'll actually notice that these two images don't even line up properly. So registration, again, comes into play as the first step of machine learning to get them in the same common space. Another example that's being used a lot is metabolism. Here what we can do is we run multiple simulations of light as it travels through brain tissue. And how it is dispersed and reflects and refracts and eventually is detected gives an indication of how oxygen is consumed. Now, for example, over here, you have a source over here and a detector over here, and you shine light, and it propagates through the brain tissue. Depending on what is picked up, you have an indication of metabolism. Now, this is a good example of how it can be clinically relevant. On the research side, this kind of example can take maybe an hour or two to simulate for 1 or 2 wavelengths of light. If you do this on a GPU with the MOC, it's now reduced to seconds. Now, suddenly you can have information back at the bedside in a minute or 2 versus multiple hours. Another example that has a nice picture, at least, is something called diffusion image processing, which is called tractography. And what you do, I'm not going to explain the process in detail, but you take a whole bunch of pictures from different angles. These are all volumes, one slice in a volume, but they've all been scanned from a slightly different direction. And they measure water diffusion. And if you take all of these images together and you solve the diffusion equation, you can build this wonderful 3D image that looks like this. Now, this doesn't actually tell you exactly where the white matter fibers are, the wiring of the brain, but it gives you a good indication of where water will diffuse, which probably is where the white matter fibers are. So why is this important? Well, if there is a tumor again, and it has pushed part of the brain aside, and the surgeon needs to go and resect that tumor, it's a very good idea to know where to go in to not disrupt major fiber areas. Again, the importance of having quick image processing available. So I'm going to take a little step down now and give you just some of the overview of what ChRIS looks like. So it consists of a couple of components. There's some kind of data source, typically something inside the hospital, and there's some kind of compute environment, which would be like the MOC. And of course, you can have multiple compute environments, and you can have multiple data sources. And essentially, all that ChRIS really does, there's one more component, which is a store, which contains all of these plugins, these compute that you're trying to run. Now, what ChRIS does is it takes input from the data source, pulls it to itself, and then pushes this out to the compute environment. At the same time, it queries the store for a whole bunch of available plugins to run and selects one of these, which it calls down into the compute environment. This crunches, produces output, which is then pulled back into ChRIS, allowing an end user to view and interact with these two data sources, both the input and output. And in the same vein, you can have more data sources come through, different compute environments, and the one central source of ChRIS is able to orchestrate between all these different environments. So in the case of the MOC, we have OpenStack over here, and then the compute controlled by OpenShift. And Dow will give some more detail about that.
Yeah, so we wanted to dig a little deeper into the technology part here. So at the top here we have BCH. That's sort of the front end of ChRIS running inside of BCH. And the bottom we have the MOC, again, OpenShift running on OpenStack. And so the way this process works is first data is sent to OpenShift through a component called the I/O handler inside of ChRIS. That's a component running on OpenShift. And then the data is stored inside of Swift. We do that because we want to separate each of the data stores on the back end so that each individual job that's running can't access data from any other job. And so we're using Swift for the segmentation there. The next thing that happens is that the process manager then gets set an operation. That operation is of the form of some Docker image to run, as well as a command to run against it. And that's the actual processing that's taking place. The first thing the process manager does is it launches a job. That job has some number of pods in it. Each of the pods have this structure. So they have first an init container that launches. In Kubernetes, that init container's job is to set everything up so the rest of the containers can then have what they need available. And in this case, the thing that it's setting up is pulling data out of Swift, writing it to some local volume, and making it available for the next container to launch. And in that case, the next container is the image processor itself, our image plugin. And the image plugin now does whatever work it's going to do. So it takes the data that's written to a local disk from an input directory, does its crunching of that data, writes the output to an output directory. And then at the same time it was launched, another container was launched, which was a published container. That published container has this entire time, since it was launched, been watching against the OpenShift API to figure out when the image processor is done. And once it is done, it will take the result from the output directory and publish it back to Swift. And then once that's done, the ChRIS front end is now able to call back into the I/O handler to get the results and show them into the front end UI. So that's the basic process. The reason that we've developed it this way with the extra two containers around the image processor is it makes it so the image processor itself doesn't really have to understand the logic around it. Pretty much every image processor that's out there now, they are written with some basic assumptions of they can read and write their output to disk. And that's really all that you have to know here. You package your image processor as a Docker image, and you are told what your input directory is, you're told what your output directory is. You do the same number crunching you've always done, except in this case, we've built it into an environment that is capable of scale. And so if we tell that job to scale to more than one instance, we only have to do one additional thing, which is rather than writing to a local volume for the image plugin, we now have to bring in shared storage. And so that shared storage now is pointed to by both of the two image plugins, and they can communicate through that shared storage or over the network if they desire. And being able to scale from 2 instances to n instances is essentially the same work. You simply specify what size you want it to run at and have your plugins coordinate with each other to do a portion of the work. So deep diving a little bit into what it's like to parallelize a job inside of Kubernetes. There are a few different options as far as how you can do the parallelization. The option that we're using currently in ChRIS is the fixed completion count. And that's because the plugins, at least that we've encountered so far, primarily use this mechanism, which is they are told how many instances are being launched. And each one of those instances will run to completion. So if we launch 100 instances, for example, and the second one fails but all the rest complete, we'll relaunch the second one until it does succeed. And then each of those are then responsible to coordinate and coalesce the results into whatever the final results should look like. And so in this example, we have some image, and we're going to break it up into quadrants. So each quadrant is handled by a single container. In Kubernetes and OpenShift by default, each of those containers would be launched to a separate node. And in that way, we can get additional compute added to the equation. In this case, it's 4, but it could be 100. It could be whatever number you can specify. The hard work here really is not so much, though, actually scaling. The hard work is writing your code in a way that's capable of breaking the algorithm up. And it really depends on what the algorithm is as to how difficult that may be. So what we did was we took an example. So there is an existing image processor out there called ANTS, or Advanced Normalization Tools. And it's a registration algorithm, so like Rudolph referred to before. And it was already parallelized. So it was parallelized to run as threads previously. And the work that we did was we parallelized it to run as processes. And once you have things split up into processes, it's very, very simple to break it up into different containers because the best pattern is usually to have a single process per container. And we did this example because we needed to prove out the system from end to end to say, what is it going to take to be able to specify both as a plugin writer and as a cluster admin what it takes to allow scale. So things like, what is my min and max scale as I register a plugin with ChRIS? And then let the cluster administrators be able to decide between that min and max, what type of scale should this particular plugin run at? And then as an end user, what priority do I want to set for a plugin as it runs? So I might tell a particular plugin should run at a high priority and it would get closer to its maximum of threads allowed, or it may be a low priority and get its minimum number of containers allowed. So we learned a lot from doing this. Again, how we scale in the system. The other thing that we learned was there are not a ton of image processors out there that are written for scale today. And this goes back to what we talked about before of the current ecosystem is not one where the image plugin writers know how to write a plugin for scale because there hasn't been a standardized platform to write against. And so the difficulty in scaling often comes down to this sort of problem where most of the time the algorithm looks something like this, where there's sort of a setup phase where everything gets in place. You sort of assign out which workers are going to do what part, and maybe some part that's not parallelizable. Then you get to the actual parallel processing part. And then after you've done your parallel processing, you need to coalesce your results. If the ratio looks something like this, you have a pretty good chance of achieving better results. However, if you have 10 hours of processing and only 1 hour of that processing is parallelizable, then you're obviously not going to get it any better than 9 hours no matter what you do. And so it really depends what the situation is as to how much advantage you can get out of it. In this case with ANTS, we did see a pretty good ratio of improvement, but it's going to vary. The other big piece of work that we've done is with GPU enablement. So just to give everyone an idea of what the topology looks like for GPUs, this is trying to break down what the setup looks like inside of the MOC with a single host example running on OpenStack. So with that host, we have 2 VMs assigned here. The host itself has 3 GPUs that are available to it. And to get those GPUs assigned to the VMs, it's a simple pass-through mechanism. So we could assign 2 GPUs to one VM, another GPU to the second VM. And then at this point, they're made available to OpenShift and Kubernetes to be able to schedule to the image processing jobs as they come up. And again, that's another pass-through mechanism. So it's a simple scheduling problem today where as a container is launched, it declares that it needs a GPU to the ChRIS system and then to OpenShift. And at that point, we are able to find a machine that has those GPUs and allocate it to particular containers. There's work that's happening to be able to virtualize GPUs, both in OpenStack and in OpenShift. But as of today, it's a simple pass-through mechanism. It's worth noting that the work with GPUs, the real innovation here, the thing that's so helpful, I've experienced at least over the past 6 months of working on this, that getting GPUs set up and working is an incredibly difficult thing. If you start from a machine and tell someone get it to the point where you're able to run a meaningful GPU workload, it's a lot of work involved. The biggest part of the innovation here is giving someone that scheduling algorithm as part of the platform makes it so that you can simply request a GPU, run your program, and a GPU is handed to you. That by itself is an incredibly major helpful thing for anyone that's trying to build one of these plugins. And again, the same thing applies really to the AI and ML work that I talked about before. Okay, so as far as in OpenShift, we use the Vice plugin mechanism. So that's Tech Preview in 3.10 that we're currently using. Hopefully we'll go GA soon. And the algorithm is very simple. We simply specify whatever number of containers we're going to launch. They are scheduled to nodes which have GPUs available, and we get to take advantage of all of that power. So we wanted to show you a couple of examples here to give you a rough idea of the types of performance improvements you can expect from using GPUs. The data is not incredibly important for you because you're not going to run this particular program most likely in whatever you're doing, but it is probably useful to get an idea of why you would go through this effort of using GPUs. And so in this case, this was a image processor that was converted to be able to run on top of ChRIS. It does prostate segmentation. And we tested it against 2 different cases. The first bar there is against a 56-core system. We can get you the specs on that if you're really curious. And you can see it took, I think, 52 seconds to run. And we compared that against running against a single NVIDIA Tesla P100, and it took 6 seconds to run. So that gives you a rough idea of the type of improvement you can get between a pretty massive machine and a single GPU. It's a powerful GPU, but it gives you an idea of why people care so much about being able to use GPU acceleration for this. And we have one more example, too.
So again, nothing revolutionary in this slide, just to belabor the point of GPU improvement. As opposed to the previous one, here, taller is better. But again, with that example of the light propagating through the brain, on a CPU, we have throughput around about this level. And running these through the GPUs, different types of GPUs over here, we just see a massive improvement. We can do a lot more stuff in the amount of time and get results back so much quicker. So we're going to quickly shift over to a demo, just to show you a little bit of a flavor for what we have there. So here I've just logged into a test version of our system back at Children's in Boston. And I'm just going to quickly show you the flavor a little bit. I don't want to necessarily get stuck into the UI. It's still a work in progress. But you would interact with a card like that. And here is some data that we've populated for a registration problem. So this data out on ChRIS as well exists in open storage, open and Swift in this particular case. And the UI over here does provide you a view to be able to look at it directly in the system like this. But now what you would typically do is you would select the data of importance, and you would select an analysis to run upon them over here, where you would choose a next step of some kind of processing. So we've done that now, and if you were to do that, let me just close that out, and execute the processing, it will open up a ChRIS viewer in a new tab. It's running, it should be running it now, and the data should be coming back in a second or 2. There we go. And this is just showing the results of that registration. So I'm just going to pull them in a little bit. So here we have our original image. And I'm going to pull in an atlas over here. And let me just show the registered volume over here. I'll just close this one a little bit. And again, as I mentioned a bit earlier, it's still loading that one image, but these are volumes. Oh, it's still trying to load that image. So these aren't just slices. It actually registered the entire volume, which consists of multiple slices. And now we can navigate through the different slices, such as this. We can compare the original to our registered by linking them together, and navigate through the volume space in a combined fashion, such as this. Just to give you a quick flavor of how the system works and how easy it is for a clinician to actually begin to interact with these very sophisticated back-end services.
Yeah, so it's worth mentioning that an end user of this will never really see OpenShift on the back end. But just to give you a rough idea of what this looks like, so if you go to OpenShift itself, this is one of our test systems that we use. And it's running, I mentioned the I/O handler before, that's PFIO-H, and the process manager, which we call PMAN, both running on OpenShift here. And then the actual jobs themselves, you will see running as pods. And so, once this comes up, so as an example, this is something that ran a little while ago. You can debug into this like you would anything running on OpenShift, and, for example, see the logs of whatever it may have done. All right.
All right, so as we're wrapping up, a couple of takeaways and paths forward. So at least for the ChRIS project, we are very excited about the work we've been doing with the MOC and Red Hat. Down in our lab, we have a very small team of developers, and there's no way we'd be able to scale to this level without technology, but also importantly without connections to the ones we've made at Red Hat and the MOC. It's really exciting to be in this space right now because a lot of stuff is happening and will be happening as data becomes more important, as medical imaging moves out from just hospitals into more larger enterprises and so forth. We've had a tremendous collaboration over the last year, and the project has accelerated beyond what we would have ever expected.
Yeah, and I want to stress on the democratizing and enabling impact of ChRIS. ChRIS is by no means finalized. We are still working on expanding it by building a larger community around it, by working with different hospitals and different healthcare application groups. And in the last month, we had a hackathon around it. There were a lot of professionals from the image processing space that came and built plugins for the ChRIS platform. But also students from my class came in and managed to build plugins for the ChRIS platform. So that's kind of showcasing the power of ChRIS. And also I want to mention a little bit about, this is the first half of the process for us. This is enabling computation and bringing it to the fingertips of clinicians. That's what we are trying to do. So all different types of image processing applications that are built out there by different researchers, now they could be consolidated in one platform and operated over using a single standard uniform framework. But also we want to address the inverse part of this problem, which is bringing the data to the application developers. So we are hoping to build a dataset repository that will have anonymized, clinically relevant data that people can work on to build and test their applications, and to also have clinically relevant problems that are proposed by clinicians, and to be able to work on real problems as computer scientists. So that's the second part of our journey that we hope to work on.
Yeah, so just to add a little bit to it with the hackathons, I think my best memory of working on this so far was at that hackathon seeing people who, again, were entrenched in building a particular image processor. And whenever they discovered the ChRIS system and what it can do, when their words were something along the lines of, oh, wow, I never thought about being able to scale my plugin before. And hearing that and then realizing like the innovation that's possible now, it was just a great experience. For me, though, working on this project, like it's a very small team that works on this project as a whole. And the amount of progress that they've been able to make, especially in the past year I've been a part of the project, it's been amazing to see it. And I think it's a really good example of being able to pick the right technologies to start with, in this case, OpenShift and OpenStack, and it really being able to leapfrog the innovation. But I just want to say thank you to Ada and Rudolph here, and to the rest of the team as well who's out there who works on this project every day. It's been a great experience. And with that, I think we'll take any questions people have. Yes, right here.
What is the advantage of OpenShift on OpenStack versus OpenShift on bare metal or OpenShift on a virtualization platform?
Yeah, so Ada talked about this a little bit. Do you want to?
Yeah. The reason that we want to work with OpenStack in MOC is because of its modular nature. But in this project specifically, OpenShift does not address the infrastructure requirements we have, like the networking, the storage, and the compute. For managing that in an elastic manner, we need OpenStack. That's why we wanted to be able to elastically move resources across different machines and be able to scale our OpenStack, OpenShift deployment whenever we need it, whenever we need something else, to be able to run that instead of OpenShift. That's why we are using OpenStack.
You couldn't achieve that with a virtualization platform?
You couldn't achieve it nearly as easily, right? So you could absolutely build OpenShift on top of bare metal, but you'd have to somehow go provide your own object store. You'd have to provide your own block storage. Like all the different pieces OpenStack brings, it just makes your life a lot easier.
Right. And also multi-tenancy, enabling multi-tenancy in an easier way, it helps us a lot in that aspect as well.
Yeah. Other questions? There was in the back?
How do you deal with HIPAA compliance?
Right. As of now,
Yeah.
yeah, as of now, this is not HIPAA compliant. All the data we have is anonymized, and we are working towards a solution that we are working towards a solution where we can build enclaves for different hospitals that are protected and that are HIPAA compliant for those systems, and also working over encrypted data sets and being able to do multi-party computation so that people do not expose their data sets to other groups. Those are all in the roadmap. We didn't talk about all the future projects we have. But as of now, our system is not HIPAA compliant.
Other questions? In the back there?
What virtualization are you built on? KVM?
It's KVM.
Okay, so for the GPU pass-through, are you having to use different brands of GPUs to do the pass-through? I've heard that as a limitation.
Not yet. So we may get there, but not yet.
Oh, so right now,
It's all one type of GPU right now.
okay, and you're able to pass that through to the different VMs.
That is correct.
Okay.
Other questions? Yes, here.
Maybe might be out of scope for this talk, but how does this change the possibilities for healthcare services at the bedside?
Well, I mean, the most obvious one is twofold. The first one is making it very easy to get new features at the bedside, right? Is without having to have anyone deal with the complexity of setting any of this up. It's available for the complexity of opening up your phone and going to a web browser. And the other part of that is also speed. Ideally speaking, the same plugins that would take a certain amount of time on a local resource inside the hospital can now benefit from much better hardware out in the cloud. And provided that the latency of pushing data out there and pulling it back isn't that bad, you have a tremendous speed up. So you can get stuff back in seconds or minutes, well, let's say minutes, versus hours. And that makes a very, very big difference. So those are the main components. And allied to that, at least, is also something that Ellen mentioned a little bit on stage yesterday, which is also important, is that a web-based container technology like this, all it needs really from the front end is a cell signal. You can be sitting out anywhere in Africa, in wherever in the world you might be. And cell signal is amazingly, it's everywhere. And you are able to now transfer images. You are able to at least interrogate data sets wherever you might be. So that's also very exciting for us.
Yes, down here.
Those plugins you mentioned, do you contribute to backup?
Yes, so we do some plugins, but the main idea, of course, is that in this huge research community where people are writing their applications, that they will containerize their apps according to the contracts that we need to have it run in ChRIS.
Yeah.
So we're not writing plugins per se so much. We're making this platform to make it available.
Yeah, but we have an image plugin
Yes.
repository that all the plugins that we have developed are freely available in a containerized manner.
Yeah, the URL was at the beginning of the presentation, too. You can go out there. Question here?
Are you able to support streaming data sources? Is it event-based architectures?
Yeah, I think the answer is not yet. It's probably something we will get into, but as of now, no.
Yeah.
Now, technically, you probably could do it by passing an ID to it and having it streamed down as part of your plugin, but as far as doing it as a feature of ChRIS, not yet. Other questions? Yes?
In the horizontal scaling side, there's shared storage.
Yes. So as of today, it's NFS. We have the potential there to convert it to be using Ceph, which also allows shared storage directly. We can't do it through Cinder today, so we're still working on that piece to make it a little better than it is, but it's NFS today.
Is there a reason you don't want to use Swift?
So the the thing there is the contract with the image processors needs to be block storage. And so we don't want the image processors to have libraries added to them and teach them how to read and write from object stores. And that's why we abstract that away from them. It's worth noting, too, the NFS shares, they're temporary. They basically come and go as each job comes and goes. So it's not important storage. It's just an artifact today that
and on that
like
point, just to follow up on that, most of the developers in this field, they don't know REST APIs. They don't know any kind of storage mechanisms like this. They just know files and directories. So we want to make it as easy for them as possible to not have to learn new models in terms of developing their compute. Most people just write this stuff in MATLAB, right? So that they just want an input directory and an output directory.
These are great questions. Anyone else? No. Lots more. Okay, down here. Okay, so it depends on how you answer the question. So I guess we can try and answer both. So there's, oh, sorry. Yeah, so as far as people in the project, there's probably two answers. There's the answer of how many people work on the ChRIS platform, and then there's the answer of how many people are building image plugins to run on the ChRIS platform. I think I can probably answer the first one of how many people are working on the project. It's somewhere in the range of 15 or so people that work on ChRIS itself. Do you have a good idea, Rudolph, on the image plugins? How many people?
So that could be certainly in the Boston area, upwards of 20, 30 people based on interest and the feedback we've had before.
Yeah, so as far as, it depends on what you're describing there. So if you mean, you can run this on your laptop, the entire thing on your laptop, and that takes a matter of a few minutes to launch it from nothing to the whole thing running. If you want to stand it up in the MOC, it's a little longer. You're probably talking a matter of a few hours to stand the whole thing up.
But really, you just have to go to Git, do a Git clone, and then run the make file, and it'll fire up all the containers. It'll be ready. It'll be waiting. You'll have the entire system, except with the OpenStack and OpenShift, but the entire system running on Swarm inside your local machine. So you can develop your plugin there, and you'll have the exact same experience as you would deploying it out to the cloud.
Other questions? Yes, here.
So you say you want to expand the community with other hospitals. Can you describe how you get on board with other hospitals?
Yeah, so far, like what we did, the process we did is just running these hackathons and inviting people so that they can build plugins and they can put it into our image repository. It is not a hospital-specific solution that we have. The other end of this is like adding another front end other than Boston Children's Hospital to this, a ChRIS front end that can tie into this. We didn't do that yet with any hospital, but that's within the plans. And hence, I don't have a direct answer of how we onboard other hospitals, but it's just that it's within our plans to do it and figure out how to do it.
So it kind of comes from two levels, right? The bottom up, which would be developers and researchers benefiting from this system in different institutions, and then it grows from that level. But also from the top, from operationally, you do have to engage with hospital admin and decision makers to get them on board with seeing the benefit of sharing their data and collaborating on a broader scale, which is much more difficult. But those are the two angles.
Any other questions? Well, yep, one more.
How did your collaboration be?
Yeah, I a little bit try to mention it. Like we are teaching this cloud computing course in Boston University and Northeastern University, and Rudolph kindly accepted to be a mentor to a student group, and his suggested project was this: bringing ChRIS to the cloud, to a public cloud. At that time, it was just running in a specific cluster, in a specific HPC cluster in the hospital. And with that class project we started, but within the last year, we turned it into a real product by especially with the collaborations, the collaboration of Red Hat. So Red Hat was a core member of MOC from the get-go. So we had a very nice connection with Red Hat. And once we brought that connection into this specific project, it bloomed into a very nice production scale environment that people can use.
It's kind of a combination of co-locality. We're all kind of in the same city.
Yes.
And serendipity. It's kind of all came together. All these different ends were looking for partners that were almost exactly complementary at the same time. So
Yeah.
that
There are
was-
also a lot of personal relations across
Yes.
the group, so that also helped.
Okay, any other questions? Well, thank you all for attending. I hope that was helpful.